Hello, my name is Diego. I'm a software engineer here at CoreOS, and I'm here to give a webinar on self-hosted Kubernetes. So a little bit about CoreOS. We are a major contributor in the Kubernetes community. We are a top 3 contributor in terms of lines of code. We lead 6 special interest groups, which are responsible for different focus areas of the Kubernetes project. And we are the creators and maintainers of etcd, which is the data store that backs the Kubernetes control plane. We also have our flagship product, Tectonic, which is an enterprise Kubernetes distribution that takes pure upstream Kubernetes and packages it in an opinionated way that we think is the optimal way to run a Kubernetes cluster. And it works across various clouds as well as on-premises bare metal. And CoreOS has a long history in containerization, starting with container Linux and extending through Kubernetes and other facets, and we have a deep experience that we draw on. So I'd like to start by just describing what self-hosted Kubernetes is and why it's an important part of how we run Tectonic and why we think it is the optimal way to run a Kubernetes cluster. So self-hosted Kubernetes defined is actually just running the Kubernetes components in Kubernetes itself as native Kubernetes objects. So for example, the Kubernetes API server, which is the main control plane component, it actually runs as a daemon set object. The controller manager and the scheduler running in deployments, and then supporting components such as secrets and config maps that are fed into the control plane are also just hosted inside a Kubernetes cluster itself. So if you're familiar with running applications on Kubernetes, this looks very similar. You might run your applications as deployments and daemon sets, etc. And here we're actually running the control plane itself. So conceptually, this is somewhat straightforward, but to actually launch a cluster and keep it running, it gets a little tricky, and so that's going to be the focus of this webinar. And then I will get into some specifics about how Tectonic uses this to perform some sophisticated operations and automate a lot of the maintenance of a cluster. So there's 3 main parts to this webinar. First, I will get into reasons why we want to run the Kubernetes control plane in a self-hosted manner and why we think this is the best way to run it. Then I will actually go into a bit of a technical deep dive of how it works and demonstrate a self-hosted control plane. I will launch one, I will upgrade one, and then I will purposely break one to show how we can use the tools at our disposal to recover a control plane and how we might actually automate that. And lastly, I will get into some of the things that running a self-hosted control plane unlocks for us. So once we have this self-hosted control plane, what can we build on top of it, and a lot of the things that we build on top of it in Tectonic that make the control plane even more resilient and upgradable and also have some other nice properties. So first, I'll get into why you want to run a self-hosted control plane. The most obvious reason is that we want to leverage Kubernetes strengths. Kubernetes is very good at running highly available and resilient software, and we want those properties for the Kubernetes cluster itself. So if possible, wouldn't it be great to use all of the logic, all of the properties that Kubernetes has to run itself? Then we don't need to create a specialized extra layer of tools to manage the control plane. Secondly, self-hosted Kubernetes really streamlines the node management story. By nodes, I mean the actual machines that are running your workloads. These could be VMs or bare metal or what have you. By running the control plane on top of Kubernetes, we don't need to have specialized master nodes that are configured and managed and upgraded separately. Additionally, cluster lifecycle management is greatly simplified and streamlined in a self-hosted Kubernetes world. And this is important because simple things tend to be more resilient, more easier to reason about, and have fewer failure modes. So it's a very nice benefit that we want to have. So taking a step back and actually thinking about the control plane abstractly, what are some of the properties that we would want our control plane, which is really the core of the Kubernetes clusters. It's what's running the workloads, keeping them running, coordinating machine resources, and so on. So this is really the most fundamental building block that all of our other applications are running on top of. So what are some of the properties that we'd want it to have? Well, one might be that we would like it to scale up and down automatically. So as our cluster grows, as our workloads get larger, we may need to increase the number of master nodes that are managing these workloads. And so it would be great if we could have something that can scale this up and down in response to the workloads in real time. Additionally, we want to be able to handle node failures gracefully. Let's say, for instance, that one of our master nodes has a hardware failure and it goes down. What we'd really like to do is spin up another machine, ideally automatically, and then replace the workloads that we've lost on this new machine. And this should happen without any operator intervention. Furthermore, we would like to safely roll out new versions. If we are upgrading our control plane to a new version of Kubernetes, we'd like to do so in a safe manner, perhaps one node at a time, making sure that that new node passes certain health checks and so on before proceeding with the upgrade. We'd also like to roll back on upgrade failures. So perhaps we complete this upgrade to the new version of Kubernetes, but then we realize that some of our workloads have failed. They're not compatible with the new version, or some other unforeseen problem has happened. We would like to roll back to the last known good state as quickly and as easily as possible. And while we're coming up with this wish list, maybe we can add a few more things. So how about advanced networking? We'd like to perhaps deploy network policies that restrict which components can speak to our control plane and in what capacity, or fine-grained controls on which endpoints they can actually talk to and which they can't. Also RBAC, which stands for role-based access controls. So we would like to create users and restrict which parts of the control plane they can talk to, and then enable audit logging and make sure that no one is performing suspicious access patterns. Also, we'd like to do health checking and monitoring. In a Kubernetes cluster, you typically want to deploy a monitoring system like Prometheus, and it would be great if we could also use Prometheus to monitor the control plane itself and make sure that the CPU and memory and disk usage is all within our expectations. Lastly, we might want to do some resource allocation and accounting. So we would like to know that our control plane is using a certain amount of resources, what it's actually costing us, if we can see the amount of compute that it's using. Also, we want to be efficient about our resources. We don't want to have to run dedicated nodes for our API server or scheduler that might be wasting compute resources that we don't need. Instead, we'd really like to follow the container paradigm and pack components as closely as possible to maximize the resource usage on every node. And so as it's becoming evident, if you're familiar with Kubernetes, these are all properties that Kubernetes provides out of the box, right? So, well, what could we use? So what would we want to use to run our control plane? The natural answer is Kubernetes. So I think I've kind of made my point a bit that if we could achieve this, this is really a big win. Next, I'd like to get into node management. So if we think about a worker node in Kubernetes, that is just a node that is running your applications, there's only a very small set of requirements, actually. First, you need a kubelet, which is the daemon that runs on every node and receives instructions from the API server which pods to run. You need a container runtime, such as Docker or Rocket, which actually runs the containers. So the kubelet will tell the runtime which containers to run in response to the API server. And you need some credentials to talk to the API server. So these are just some small public key infrastructure type credentials that the kubelet will use to authenticate with the API server. And that's it. So it's actually pretty simple, and managing this is not that challenging. In a self-hosted world, that's all you need for masters as well. Since the masters are just running as native Kubernetes objects, we don't need to specialize how we deploy the API server, the scheduler, how we upgrade them. We don't need to perform additional automation using other kinds of automation tools. We just use Kubernetes itself. We use kubectl or other standard Kubernetes tools to deploy and upgrade our control plane. So to get into the technical bits a bit, how do we actually select master nodes? It's actually simple. All we do is add labels to nodes that we want to run master workloads on. For example, we could say kubectl label node n1 master true and set a node to master, or we can at startup time tell certain kubelets that they're masters. A really nice side effect of this is that any node can become a master at any time. So let's say our cluster is under high load and one of our masters goes down. And since we have monitoring, we get an alert, and we, as an operator, might want to go and debug this. As a first step, while we're trying to recover a node or start up a new one, we can actually commandeer a worker node by labeling it as a master, and then it can take over some of the workloads from the master nodes temporarily in order to help keep our cluster stable until we have a more permanent mitigation. The last reason why we like to run self-hosted Kubernetes clusters is streamlined lifecycle management. So installing a cluster, you might make some choices about which kinds of settings and flags you want to use to match your environment, but those might change over time. Additionally, you want to upgrade a cluster to newer versions of Kubernetes as they come out, and so on. And so making all these changes should be easy and straightforward, and we should be able to rely on the underlying infrastructure to actually propagate those changes out. And so in a self-hosted world, it is easy. You can use things like kubectl apply, or also programmatic access to the Kubernetes API in order to make changes. And so I'll get into this a little bit later in the hands-on demo. And at CoreOS, in Tectonic, we build a lot of automation on top of this because we have the self-hosted control plane running. We can do automated upgrades. We can do automated self-healing. We can do automated customizations because we can encode this logic programmatically. And I'll get into this a little bit later as well. So now that I've made the case for why self-hosted Kubernetes, we believe, is the best way to run a Kubernetes cluster, I will actually go into the technical details of how it works, how we were able to achieve this, because there are some technical details that are a little bit tricky, but all solvable in the end. So there were three main challenges that we had to solve in order to make self-hosted Kubernetes a reality. The first is bootstrapping. So as it might seem clear, we want to run the Kubernetes control plane as Kubernetes native objects, but that requires having a Kubernetes cluster in the first place. So how do we solve this chicken and egg problem? How do we create a cluster from scratch? Once it's running, then we're in a steady state. Then we can keep upgrading it and changing it. But to get it started is a tricky problem. Next are upgrades. So Kubernetes as a project is moving very quickly. And at CoreOS, we like to keep up to date with upstream Kubernetes as much as we can. We're usually following the latest upstream releases very closely, and so making upgrades quick and painless is important, so I'll kind of go into how that works. And then lastly, disaster recovery. So things can and do go wrong, either due to operator error or due to machine failures and so on. And so I'll go into some of the ways in which we solve disaster recovery problems in the self-hosted world. So starting with bootstrapping, I'll give a brief overview of how it works. So the control plane, as I mentioned earlier, runs as daemon sets and deployments, which are native Kubernetes objects. But we need a control plane to create daemon sets and deployments. So how do we do this? Well, we're going to have what I call clever hack number one. So I mean hack in a good sense. It was a nice insight that one of my colleagues at CoreOS had, which is that we can create a temporary static control plane to bootstrap a self-hosted cluster. And what this means is we will create a one-time, very specific control plane on one node, and that will then be used to pivot into a self-hosted, self-sustaining control plane. So how do we do this? There are a few different projects that do this, and one is called bootkube, which is one that CoreOS contributes to heavily. And so what it does is it takes a set of temporary control plane manifests. So these are Kubernetes manifests written in YAML or JSON that describe how this temporary control plane will work. It has self-hosted control plane manifests, so this describes your actual steady state control plane. And then you need one initial master node that is going to be your bootstrap node. The bootkube project takes these as inputs. It launches a temporary control plane on that master node, and then it uses that to create a self-hosted control plane, which then takes over. So I'll actually launch a control plane now and demo for you. So on my machine here, I have 3 nodes running as VMs. We have an etcd node, C1 is our master node, and then W1 is our worker node. And then we have our assets, which is the second thing I described. So we have a kubeconfig, which is the credentials we use to talk to the kubelet. We have the bootstrap manifest I mentioned, which is for the temporary control planes. We have a temporary API server, controller manager, and scheduler. And then we have the self-hosted manifest, which you can see are considerably more. So this actually describes the self-hosted control plane. So there's the API server, the controller manager, the scheduler, and we have a few add-ons. We've got the proxy, we have the kubeDNS, and then we have a few things that are also interesting. We have kubeflannels. We're actually deploying our network overlay. We're using flannel in this case at the time that we create our self-hosted control plane. So our self-hosted control plane will actually be communicating over the overlay network. And then if we scroll down, we just have all of our key material that we need for etcd and for the API server for everything to communicate securely with each other. So now if I SSH to my master node, here I've already copied over bootkube and the cluster assets, so I'll just launch my cluster. So say sudo bootkube start, and then I say dir is for a cluster. And so what this is going to do, if I switch to a new terminal, is it's going to copy the bootstrap manifest that I showed earlier to the Kubernetes kubelet manifest directory, which the kubelet will then use to launch local static pods. So these are just this is a feature of a kubelet that if you put manifest in this directory, it'll launch pods. And this will create the static control plane, which will then be used to pivot into the permanent self-hosted control plane. So if you look at back at bootkube, it's actually completed. So it created all these self-hosted assets, and we have a self-hosted control plane. And once that completed, it stopped the temporary control plane, and the self-hosted control plane took over. So if I look back in that directory, it's empty except for this checkpointer thing that I will get into later, and we're actually running a self-hosted control plane now. I'll go into the details of how this process happened, since it happened a little quickly in the terminal. So when we started out, we had etcd node that I showed, we have bootkube, and we have the kubelet that's running on our master node. So the first thing bootkube did was it created static pods by copying them into that directory, as I showed. The kubelet watches that directory and creates these static pods, which are Docker containers. These pods talk to our etcd cluster that is already running. And then the kubelet is configured to talk to this API server. And so once the API server is running, the kubelet joins, and now we have effectively a one-node Kubernetes cluster. Once bootkube detects that this cluster is ready, it creates the self-hosted components by talking to the API server, which stores them in etcd. And then the kubelet, since it is part of this cluster, is notified by the API server that it needs to start these new pods, and so it does so. And so our self-hosted control plane starts running. And once bootkube detects that the self-hosted control plane is completely up and running, it stops the temporary one. At this point, bootkube is done. The self-hosted control plane is talking to etcd, and the kubelet joins the cluster talking to the self-hosted control plane. So we can kind of show this here by using kubectl, which is the command line tool for Kubernetes. So first, let's look at the nodes. So we have two nodes right now. We have a master and a worker, and you can see that the master has its role identified as such. And then we also have the self-hosted control plane, which is in the kube system namespace. So we have daemon sets, kube API server, kube flannel, kube proxy. And then we also have deployments, this controller manager and scheduler. So that's our self-hosted control plane. And next, I'd like to go into upgrades. So this section is actually a bit boring, at least in the simple case. If we want to upgrade a component of our control plane, we can simply use kubectl edit and go and change the image field in the manifest, just like if we're managing any sort of application. So let's go ahead and do that. I'm going to upgrade our API server. So it's running Kubernetes 184. Let's just upgrade it to 185. And that's it. So if I look again at the API server, you can see it wraps around here, but it's changed to Kubernetes 185. And if I look at the pods, yeah, the API server, it's restarting, so it says it's an error state right now, but it will come back in a second, and we'll have a fully upgraded cluster here. One more thing I'd like to say about upgrades, though, is that obviously upgrading this manually doesn't scale for a large production cluster. It's not a good process for this, and so this is where the automation comes in, where you could see that instead of someone running the kubectl command on their laptop, we could be running software that communicates to the Kubernetes API server and performs this upgrade. Next, I'd like to get into disaster recovery. So as I mentioned earlier, things do go wrong in production. That's a fact of life. And so we want to make sure that self-hosted Kubernetes is resilient to possible failure scenarios. And there's three main failure scenarios that I'd like to get into. First is a partial control plane loss. So let's say, for example, that due to operator error, one of the components of our control plane goes down, but our cluster is now not functional as a result. Well, then we need to recover that individual component and get our cluster back to a healthy state. The next failure mode would be a total control plane loss. So let's say that I'm running a cluster and I have a complete power outage and my backup batteries go down, and so I've had to reboot the whole cluster from scratch. Well, since it's self-hosted, we still have this kind of perpetual motion problem where we need to start the cluster back up. So we need a mechanism to recover the entire control plane in that kind of outage. And the last scenario would be a total cluster loss. So if I have some sort of catastrophic failure where I lose all of my servers, then I need to recover from that. And in that case, you'll have to recover from a backup, obviously. So before I demonstrate a failure mode and recovery, I'd like to make a digression to talk about the pod check pointer, which is an important part of self-hosted Kubernetes being resilient to failure. If you were looking during the upgrade demo, you might have noticed a little bit of a trick. And there's two aspects to it. One is you saw that the API server was failing to come up temporarily, but I was actually able to see that. And then also I'm only running one API server. So what is happening there? How was I able to upgrade an API server? That means that one needed to stop and a new one needed to start. And so for a brief time, there was no API server at all. Similarly, how do we handle master node reboots? If I only have one master node and I reboot my system, how will it come back up? The answer is that we run a special daemon called a check pointer that runs static pods when the control plane is non-functional. So much like how bootkube used static pods to create the initial self-hosted control plane, this check pointer acts as a babysitter that is taking critical control plane components, making snapshots of them locally on disk, and then detecting when they're not running, even though they should be, and deploying the static manifest temporarily in order to have the critical component recover. And so I will illustrate this with a diagram here. In the steady state, we have our kubelet that's running pod 1 and pod 2. Our API server says that we should be running pod 1 and pod 2. And so our check pointer, which is watching this, has inactive checkpoints for pod 1 and pod 2, these critical pods, and no active checkpoints. Now, for whatever reason, pod 2 has stopped running. This could have been due to a reboot or another issue. If it just failed and relies on actually its own presence to restart. So let's say the kube scheduler is what schedules pods. And so if pod 2 is the kube scheduler and it's gone, there's no more kube scheduler to tell it to schedule. So what happens now? The check pointer detects that pod 2 is not running, even though the API server tells it that it should. And so it takes its checkpoint and deploys it. This causes pod 2 to start back up in the static manner. And hopefully that is enough for the regular pod to come back up. And then we can retire the static pod. So this diagram might seem familiar because it looks a lot like the bootkube bootstrap process, and that's absolutely correct. And then we're just back to our steady state. So with the pod check pointer illustrated, I'll get into bootkube recover. So the check pointer helps us with some of these situations I mentioned, such as rebooting a master node, but it doesn't help us from all outages. There are certain failure modes that can't be solved by the check pointer, and some of these specifically might be either operator error or misconfiguration or just larger scale outages. So if only there was a way to jumpstart the cluster. How could we take a cluster that has been running and just, much like a car, give it a jump start? Well, jumpstart sounds a lot like bootstrap, and so perhaps we can use bootkube to rerun the static control plane and allow the cluster to recover itself back into a good state. And so that's exactly what we do. And I'll give a quick demo of this. So just checking, our cluster is back into a healthy state. We have this API server that's running. Everything is good. Now, let's say as an operator, I'm trying to scale up my kube scheduler because I've been alerted that it's overloaded. So I do kubectl. I say scale, but instead of maybe I want to type 10 replicas, and I type 0. Okay. Kubernetes happily does that for me. As you can see, now it is terminating my schedulers. If I look one more time, still terminating. Watch this until it's done. Okay, there's no more kube schedulers. Well, obviously that's not what we want. We realized we really wanted to have at least 2. So what happens when I scale it back? Okay, the API servers told me, okay, you changed your deployment. You now have 2 replicas. It's just like scaling any other application, except wait a minute. Kubernetes uses the kube scheduler to actually schedule these pods. And so since there's no kube scheduler running, we've gotten into a big problem, which is these pods can't schedule. We don't have a scheduler anymore, and our cluster actually is unable to schedule any pods. It's in a broken state. So what can we do? And the answer here is to use the bootkube recover mechanism that I just described. So if I go back to my master node, I still have bootkube. So what I'm going to do is I'm going to run bootkube recover. And in recover, it takes 2 arguments. The first is recovery dir, which is where we want to recover our assets to. And then a kube config, because we want to talk to the control plane to extract these assets. Okay, so it's recovered assets from the control plane, and we are ready to use them to jumpstart our cluster. So we're going to, once again, use bootkube start. But this time, we're going to point it at the recovery assets that we just extracted. And so it's running a temporary control plane now. We're not actually creating any self-hosted assets because they already exist. All we really want is a temporary control plane that is going to allow our cluster to recover itself. So if we watch the pods again, I'm still on the node here, sorry. We can see that the kube schedulers are running again, and we are back to a happy state. So that's an example of recovery. Okay, so now I've described the mechanics of how self-hosted clusters work, and Tectonic has been using this for over a year now, and we think it works very well because of all the properties I mentioned. So now I'd like to get into what we can accomplish on top of a self-hosted cluster. So now that we have Kubernetes running in self-hosted manner, it gives us all those nice properties we already mentioned, but it also unlocks some extra things that we can build and are building here at CoreOS. So the first is automated operations. Kubernetes enables a lot of automation. It has a rich API. It has a lot of core components and add-on components that allow you to manage your workloads. And so it's really nice that we can use these to manage your control plane as well, since again, it's the most fundamental part of your Kubernetes cluster that is making sure that all of your other workloads run reliably. So the first thing is cluster upgrades. We upgraded a component manually, but really what we want to do is use client Go, which is the Kubernetes client library, to perform upgrades in a safe and reliable manner. We want to make sure that we have fine-grained control over how we roll things out, in which order we control things, we upgrade things, and then also if there are any pre- and post-upgrade operations that we want. And so this is something we do in Tectonic. Another one is kubelet upgrades. So kubelets are running on all of our nodes, but we can actually run a daemon using a daemon set, which is a Kubernetes object, that manages the upgrades of those as well. It can install a new kubelet, it can actually upgrade the container runtime, it can manage everything. And again, this is running as a Kubernetes component. And then configuration management. So clusters are dynamic things change over time. Kubernetes releases new features and we want to be able to turn these on. So some things we like to do are change our control plane to match changes in our environment, to enable new features that come out in newer versions of Kubernetes, change our network settings, or if we're using a network overlay and we want to enable new policies or upgrade it. These are all things we can do very easily because they're just native Kubernetes components. And these are all things that we're doing and that Tectonic does right now. The other aspect is node management. The nodes that are running your Kubernetes cluster are very important, and so there are nice things we can do with our self-hosted Kubernetes cluster. The first is self-healing. So an operator can communicate with a node agent to perform recovery operations. So I demonstrated using bootkube recover manually, but that was suboptimal. I as an operator had to SSH to my node. I had to run those tools. It required human intervention. But there's nothing preventing this daemon that is running on every node to detect and recover from these failure scenarios using those exact same mechanisms. They're very automatable. Next is autoscaling. As I touched on at the beginning of my talk, we can provision and deprovision masters as needed by just changing labels. So something that newly joining nodes can ask when we provision hardware is, what should I be? Do we need another master? Do we need another worker? And so this is something that, since by the dynamic nature of nodes in a self-hosted world, we can accomplish this very easily. And lastly is node identity. So Kubernetes supports something called TLS bootstrapping. And in self-hosted clusters now we can have each node generate a unique identity as it joins the cluster. It gets its own certs for that, certificates, and then it can rotate them. So that's a nice feature that is, again, very easy to achieve in a self-hosted world because the nodes are very simple. And that's all I have, so I will turn it over to answer questions. Okay. So first question is what a static pod is. And so sorry if I kind of breezed through that. I think I touched on it a few times. But the difference between a static pod and a regular pod in Kubernetes is that a static pod is defined by a manifest on disk. And so I'll step back and say, what is a manifest? A manifest is the declarative way in which you define an application in Kubernetes. So if I want to run a web server, I create a manifest that says, create a deployment of Nginx, and here are the arguments that I want to pass to Nginx, and deploy it. Now, typically in a Kubernetes cluster, you send these manifests to the API server, and it manages them directly. However, in the absence of an API server, the other way to run these manifests is to put them on the kubelet itself in a special directory that it watches. It reads the manifest and it runs it locally. And so the way that this comes into play in self-hosted Kubernetes is during these modes I mentioned of either bootstrap or recovery, where the function and control plane isn't present, there's no API server, or other component, and so we need to have the kubelet run the pod directly. So hopefully that answers that question. Next question is whether basically have a backup Kubernetes with static stuff. So the answer to that is yes. In some sense, that is how it all works. We are using a static control plane as a kind of jumping off point to start the self-hosted control plane or to restart the self-hosted control plane. And so I think that's an accurate way to put it, but it's fairly simple and it works, and so it's the best mechanism we have for running this control plane. So in my example, the question is, was etcd managed by systemd in my example, or was it a container running under the container runtime? So the answer is both. In container Linux, we run everything as a container. So in this case, we are running a dedicated etcd node that is running a systemd unit that launches an etcd container. But there are different ways to run etcd. Since I'm using, in this example, I was just using pure bootkube. That was the way that we launch bootkube for these examples. The way we run etcd for these examples. But the only real requirement is that you have a functioning etcd cluster, and you can run it any way you like. Next question is, are there any benefits in migrating a self-hosted Kubernetes? I'm not sure if I fully follow. I'm assuming you might ask whether there are benefits in migrating to a self-hosted Kubernetes cluster. I think we at CoreOS think that self-hosted Kubernetes has all these benefits that I've described. So I would say yes, there are many upsides to moving to a self-hosted Kubernetes cluster. Perhaps an example of this is that kubeadm, which is the Kubernetes upstream canonical cluster creation tool. So there are many distributions of Kubernetes, of which Tectonic is a significant one, but there's also a pure upstream tool called kubeadm, which demonstrates how to launch a cluster. And it's, from one cloud to another is the follow-up question. So I'm still not quite following the question. Migrating from one cloud to another, I'm not sure. That probably depends on your requirements. For us, we support multiple clouds, and so what we actually strive for with Tectonic is to support running. You can run a cloud in AWS. You can run a cloud in Microsoft Azure. You can run a cloud in bare metal. And since they're all running Tectonic, which is pure upstream, you're going to have the same kind of Kubernetes cluster in a consistent view, so you can run your applications preferably unmodified on all of those clusters. But maybe I'm not following the migration question here. I'm going to move to the next question, which is, do you have a best practices white paper document to implement a good Kubernetes cluster? I would have to follow up on that. If you'd like to email info@coreos.com, we can direct you to the white papers we have. There's a lot of best practices, and it's moving very quickly, so I'd have to get the latest. So let's see. So I'm going to try to answer this one here. If you have a reference architecture you can share with us. Yeah. So same answer. I would love if you reach out to info@coreos.com. That's something we can provide for you. What are the best resources sites to start learning the path for Kubernetes? So there are a few places. The Kubernetes homepage actually has a list of getting started resources. Then depending on your preferences on learning style or how deep you want to go, you can choose different ones, ranging from something called Kubernetes the hard way, where you deploy each component from scratch by yourself, to launching. There's also a tutorial where you launch a cluster locally. You can also install Tectonic. We have a sandbox, and we have a 10-node free license if you want to use Tectonic and play with a self-hosted cluster. So I would recommend going to the Kubernetes homepage and seeing their resources, and also launching a Tectonic cluster, because we work very hard to make it easy and seamless to do so. So let's see, earlier you mentioned multiple projects implementing self-hosting and bootkube being one, or other projects. So the other main project is kubeadm, and kubeadm has added self-hosted for launching clusters and is working towards adding self-hosting support for upgrading clusters. Again, it's because I mentioned that they see self-hosting as a good way forward for launching a cluster, and so those are the two main projects that I'm aware of. Other people are deploying self-hosted clusters using bootkube, much like Tectonic does, in their own, perhaps private projects that we're not aware of. Okay, the next question is, do I need CoreOS to achieve the described in the webinar? So I should have been more explicit about this. So I actually was using bootkube, which is an open source Kubernetes incubator project. In the slides, there's a link to it. And so I wasn't actually running Tectonic at all. I was using container Linux for my nodes, because that's what the examples use. But container Linux is separate from Kubernetes and Tectonic. So no, you can use bootkube if you want to play around with this, but I also recommend using Tectonic Sandbox or a 10-node cluster, because you get a lot of other nice benefits as well, and it's no harder. In fact, it's easier to launch than using bootkube. Okay, I think I answered that one. I answered that one. I think I answered that one. Okay. Let's see. What would you say about the main advantages of Kubernetes over other solutions? Well, that's a big topic. I would say I'll speak to the advantages of Kubernetes, because I think there are a few that I think it just speaks for itself without having to compare necessarily. One is just adoption. So Kubernetes has grown immensely. It's getting, I think, the largest market share in terms of data center automation. There's a lot of momentum around not only running Kubernetes, but running applications on top of Kubernetes with things like Helm, and then also monitoring with things like Prometheus, which is another CoreOS project. Tracing, there's work on things like Jaeger and other tools for introspecting your applications and workloads. And then service discovery is another big topic. So there are tools like Istio that allow you to run service meshes and have service discovery. So the ecosystem for Kubernetes is very healthy and very strong and growing very fast. And so I think that in of itself, Kubernetes is maturing as a project. It's got the backing of Google, Amazon, Microsoft, CoreOS, lots of large companies, lots of small companies, but then also just the ecosystem is large and healthy, and that really helps if you're running applications to have resources and tools at your disposal. And I don't think that other tools have that same momentum right now. So that would be my case for Kubernetes. Obviously, we're a little biased. Well, thank you very much, anonymous person. And then lastly, is kubespray deployment based on the same bootkube jumpstart method? I'm actually not sure, but I don't believe so. So I'd have to follow up. But I'm fairly certain that kubespray does not. Again, the main components I know that are using self-hosted are bootkube, which is used by Tectonic, and then kubeadm. All right. So I think that's all the questions. Thank you, everyone, for attending, and yeah, have a great day.